Hey everyone, I'm Kirby. This is Kirby Meets Audio, and today we're going to talk about the wide, wonderful, fun-filled world of crossovers. So this is the second video I'm doing in a series of videos on designing DIY studio monitors. So if you haven't seen the first video, you should go watch that. I'll put a link right here and down in the doop. This video is going to make much more sense if you watch that one before this one. In that first video, we basically planned out our build. We picked drivers. We designed our enclosure, and that somehow took a half an hour. I don't know. I want to do a final crossover design after I've built the enclosure, have the drivers in the enclosure, and then I can actually measure it myself because I want these to be relatively flat. But I want to do this crossover design just to make sure that there's not gonna be any hiccups down the line. This is just kind of a test to make sure all the drivers work together properly, and then we'll see how it goes. But we'll talk about three-way crossovers in this video, and you can watch my design process a little bit. But while we're here, thank you so much, everyone. If you watched that first video, it's doing really well, and that's really cool. It's been a while since I've had a solid performing video, so I appreciate it. So in my excitement with all those views, I did something I don't normally do, which is I actually looked through the comments and have been looking through the comments over the past week. But you guys, you brought up some good points. Point number one, I was calling the Dana Audio. I don't know why. I got in my head that it was Dane Audio. Point two, while I was talking about the different kinds of monitors that are in a typical studio, I was talking about artists or moneymen monitors, or in other words, mains is another term for it. Yeah, those are mains. I was calling them those because I was being cheeky. I don't know, I was having some fun with it. But I didn't want to make the impression that those main speakers are solely for impressing clients. Although I do think one of their main reasons is to impress clients. They're used to do a wide variety of things during a session. And every engineer, recording engineer, mixing engineer, uses different monitors for different reasons. And there are more than two types. I was just generalizing. Three, I didn't want to make the impression that it's easy in any way to design top tier speakers, especially studio monitors. High-end speaker companies, whether it's studio monitors, reference, hi-fi, whatever it is, if it's at that upper echelon, those companies are investing loads of money and time into making those speakers as perfect as they can get them for their goals. That is not what we're doing here. And basically never what I do on this channel or through any of my builds. I'm all about hitting that 80% mark. It's really hard to get to 99% of perfect speaker quality, but hitting that 80% is 100% doable by you, me, anyone. As long as you have the right information and you take the time to study, do your work, put in the effort, you'll get there. And let me tell you, 80% is a really, really good sounding speaker. Really good. I also want to clarify what these monitors are going to be used for. These are not going into a dedicated recording studio. These will be for my setup here to listen to music and to produce my own music. There's a difference between mixing and recording studio monitors and what we're doing here. I'm doing more of a generalized production monitor and computer music listening setup. Now, that doesn't mean that they can't be used to reference recording, to monitor recording, to mix, to do any of that stuff. They're just not designed specifically for recording, for mixing. They're a little more general. I think we should do a design series specifically for dedicated recording studio monitors. If you want to see that, you know what to do. Comment. I really appreciate you guys commenting. It's like the discussions that we can have in the comments is really fun, and your feedback on what you like and what you want to see, that's good. Keep doing that. Comment. Go right now. Comment something. Comment what project you want to see next. What you hate about what I'm doing. What's your favorite color? Just comment. It helps. It's good. Let's talk about stuff like colors. All right, enough of that. Let's talk about crossovers. Our speakers are a three-way speaker design. That means they have three driver types within one enclosure. They have a tweeter, they have a midwoofer, and a woofer. The tweeter is specifically designed to handle the upper ranges of the full frequency spectrum. The mid-range handles the mids, and the woofer handles the lows. So to make sure that each of those speakers only gets the portion of the frequency spectrum that it needs, that it wants, we use something called a crossover. And in our case, we're doing a passive crossover, which means we're using passive components, capacitors, resistors, inductors, to cut off frequencies up to a certain point, depending on which driver it's going to. If you want to know more about the specifics of crossover design and what crossovers actually do, check out this video right here. I have a few videos and I think a whole series on crossover design. Go look at those if you're confused or don't know, or you're starting at like the beginning, you don't know anything about this stuff and you want to learn. So we're going to be using a program called VitUX CAD. I'll put a link down in the description. It's free, it's really powerful, it's a great crossover designer, but it's also deeper than that. It has some enclosure, some baffle diffraction calculators, there's a bunch of stuff in here. Suggest you check it out. Doop doop. All right, so one of the reasons I like to use Dayton Audio drivers is because Parts Express tests and records the FRD and ZMA files for each of their drivers and makes them available on their website. And you use those files to simulate the drivers in software. So if you're not using Dayton Audio drivers, you can use products to record the files yourself, or sometimes you can find the FRD and ZMA files online, like other people have done that work for you, recorded them and uploaded them. I'll try to find there's some like repositories, databases that have a lot of measurement files available to you. I'll put a link down in the description. So I've got my tweeter loaded, my midwoofer loaded, and my woofer loaded. Refer to the last video if you want to see the specific drivers that we chose. So the first thing I'm going to do is go over to crossovers, and this is where you're going to build your virtual crossover. One thing about this software that's great for beginners is they have a library of default starting points for crossovers that you can load up and change to make work for you. So under this tab, we have a whole bunch of different crossover types. So if you're making a two-way, we've got some two-way stuff, all your high pass, your low pass filters, notch filters. One thing I like to do is use their library as a starting point. We're gonna start with the tweeter. So we're gonna need a second order high pass filter. So we want all the frequencies above a certain frequency to pass, the highs to pass and the lows to be shut down. So we're gonna do high pass second order passive. This is what it looks like, and it's gonna give us these parameters just to start with. So we're gonna hook that into, this is our power source, by the way. Now we're gonna get one of our speakers. We're gonna start with a tweeter. If you wanted to change it down here, you can change it to the mid or the woofer, and then everything needs to be grounded. So this is your positive, your negative, and this is a ground. We're gonna want a resistor on here. Boom. So now we have our frequency graph of our tweeter with a crossover point of 3,500 Hertz. So with the mids, we want to cut off the lows and the highs. So we want our high pass plus low pass second order. So these numbers really mean nothing to you. This is just default numbers, so don't worry about that. Connect it up to our mid-range. You see it looks all wonky, crazy, because those numbers are just random numbers. Or they were used for some other speaker other than ours. Now we're gonna do the woofer. All right, so there's a few different orders when it comes to crossovers. You might have seen that I was saying I'm using a second order low pass filter. Normally I start with either a first order or second order. Usually it's second order. If I can turn it into a first order, that's great. If I have to go up to a third order, that's okay. I don't normally go up to a fourth order. As you increase the order, you increase the steepness of the cutoff. So as you can see right here, let's see this red line. This is our tweeter. This slope is how quickly it gets cut off from the rest of the frequency spectrum. So only the frequencies above this point get any sound at all, and you're really only gonna hear starting up here or so. So the higher you get in order, the faster the cutoff, but the more components are needed. So it's gonna increase costs. It also increases the components in your signal path. You wanna keep that as minimum as possible. Both of those things, really. So as we said, the tweeter is this red line, this green line is the mid-woofer, and the blue line is our woofer. This gray line is the sum of the frequencies of all of our woofers. So the gray line is the final sound that we're gonna be hearing from the speaker, and that's what we really wanna pay attention to. On the left side of the graph is our dB range, or amplitude, or volume. Bottom of the graph is our frequency spectrum. So we start down here. On the left side is our lows at 20 hertz. On the right side of the graph is our highs at 20,000 hertz. And on the right side of the graph is our phase or alignment. We're not gonna really be talking about that in this video. All right, now let's talk about these symbols on the left side of the screen. This rectangle represents a resistor. These two lines represent a capacitor. This loop-de-loop symbol represents an inductor. And this is your driver. I'm not gonna go over specifics on what each of those components do for your crossover. Again, I have like really in-depth videos on all that stuff. Go watch them. So on this tweeter, we used our library blocks to give us a starting point of where the crossover point should be. It gave us this really wonky graph. We need to change it. On the graph, when I change this number, stuff starts to happen. And this is actually what's really cool about crossover design using a program like this. Crossover design is just messing around with all these different parameters until you get what you want. And anyone can do that. Like you can load up your drivers into this software and spend a half an hour just tweaking, and you'll start to figure out what each component does to your graph, how it relates to the other components in your crossover. And eventually you'll probably get to something that is better than where you started. And you'll learn along that process. And really the only thing that separates a good crossover designer from a brand new crossover designer is intuition and experience, which just quickens the process. Like a lot of it is just trial and error, noodling around, seeing what works and what doesn't work. And that's exactly what I'm gonna do now. So you might have noticed at the beginning that I put resistors on the tweeter and the woofer. And that's because the lowest sensitivity driver that I have is the mid-woofer. So resistors impede the flow of electricity in a circuit. So putting a resistor on the tweeter and woofer, those two being the highest sensitivity of the three drivers, will lower their sensitivity to match the mid-woofers. Another little tip is to save your work along the way. So if I get to a point like I'm at right now where I'm pretty happy with where it's at, but it definitely still needs some work. I want to keep noodling, but I don't want to mess up what I've already done. Like I want to try some new weird noodling. Down here under variants, you can start a whole new graph without it affecting your previous work. So I have a whole bunch here. I just started R6, and if I delete this whole section and mess up my graph, back up at R1 is where I copied it from. That's not affected in any way. Save your work as you go because you want to experiment, you want to try stuff that might not work, and you don't want to lose the progress you've made. So if you ever run into trouble like I'm having in the crossover point between the mid-woofer and woofer, you can go back to the driver section, click on your woofer, and down here there's invert. And that's gonna switch the polarity of your driver. And what that does is instead of taking away those frequencies that overlap, it's gonna double those frequencies that are overlapping. And you might find that works better for your crossover. All right, so you might get to a point where you're happy with your work. You're happy with your graph. It looks good, it's pretty flat, or whatever your goals are. Unfortunately, this is all best case scenario. Up to this point, you didn't have enough information to put in all the variables needed to make the graph as accurate as possible. So there's two things. One thing is that all the values for the capacitors, for the inductors, just because you were able to put those values into the computer doesn't mean you're gonna have that value available to you to purchase as a physical component. So really this is a two-step process. First step is figuring out what is possible. Second step is rooting that possibility in reality. So now we're gonna take those values that we've come up with and match them with components that we can actually purchase. The second thing, and probably the bigger issue, is that inductors have resistance. When we started, we didn't know what values of inductors we're gonna need for this project, so we didn't know how much resistance they were going to put on the system. Now that we have a better idea of the values that we're gonna need, we can put in the actual resistance of those inductors, and that's gonna change our graph quite a bit. All right, so let's start with the tweeter. We want a 4.7 microfarad capacitor. So let's look at our capacitors, and oh, wouldn't you know it, there's actually a 4.7 microfarad capacitor. Boom, ready, done. That isn't always gonna happen. Also for the tweeter, we're gonna need a 0.16 millihenry inductor. So as you can see, we don't have a 0.16, but we have a 0.15, which is very close. So we'll look at those. So an inductor is basically a coil of wire. The wire used to make that coil, it can be a different gauge and still create the same value. So the thinner the wire, the higher the impedance, but the less expensive the part is. Thicker the wire, the lower the impedance and the more expensive the part is. So I like to start with the least expensive inductor, add that into my graph, see how much it affects the graph, and then move up in gauge from there. So this inductor has 0.26 ohms of resistance. So we're gonna click on our inductor. Down here is our ohms. And we're gonna change it to 0.26. That didn't affect our crossover very much, so that's fine. No worries, we can use the cheaper inductor, all good. That's gonna change when we get to the woofers, but stay tuned. So now for the mid-woofer, we need a 110 microfarad capacitor. Let's take a look. So the highest capacitor value available is 100 microfarad. So if the value in capacitor you need is above 100 microfarads, you can put two capacitors in parallel, put them side by side, twist the ends together, and they will sum their two values. So if you put 200 microfarad capacitors together, you'll have a 200 microfarad capacitor. Make sense? Cool. Or in this case, if we really wanted 110 microfarads, we can use 100 microfarad and a 10 microfarad parallel, boom. All right, I'm gonna go through and find the equivalents for all these values, and if anything crazy pops up, I'll let you know. All right, so when you get into the woofers, with the larger inductors, you're gonna have much higher resistance within the inductor. So this 6.8 millihenry inductor has over 1.5 ohms of resistance in it. So as we add that to our graph, take a look. Oh, it just did it right there. There's a big drop. So crossover design is a two-part process. It's the fun fantasy part and then the reality part. And you really have to redesign most of the time. This is actually looking pretty good, but most of the time you will have to redesign or continue to design your crossover after you put in the reality numbers. So now that you put in all your reality values, your inductors are closer to what they're going to be at the end. So now you can use these more refined values to start noodling once again and continue to find that flat frequency. Now, once you do find that flat frequency, you're gonna have to go back, do the reality check again, and start adjusting. And you can see how this is an iterative process. All right, another little tip. If you get to a point where you're pretty happy with your progress or you hit a roadblock and you can't seem to do what you want to do, save, get up, have lunch, have a drink, do whatever you want. Let your mind think about other things, come back, sit down, and usually you'll figure out what happened just by messing around again. Full disclosure, I actually did this before recording and just did it again for you guys and came up with a graph that's just a little bit better than what I did before. Just totally, you know, just noodling. That's also a cool thing. You give the same drivers to 3 different designers and you'll probably get similar, but 3 different crossover designs. So as you can see on this graph, this line right here is 85 dB. This line is 90 dB. So each of these little marks in between those 2 darker lines, the gray lines, that's 1 dB difference. So if we're using 86 dBs as our kind of reference, which is basically right down the middle, this full graph is within 1 dB, except for right here and down here, but noodle within 1 dB of being flat across basically the whole spectrum. It's pretty good. And that's what we're looking for. All right, so that's the preliminary crossover design process. So I'm gonna use this information to order my parts. I know they're gonna work pretty well together. I'm gonna get this crossover components and we'll put it together in the next video. If you guys have any questions about this process, or if I left something out that you are confused about, hit me up in the comments. I really appreciate your guys' comments. Give them. Talk shit. I don't care. Just comment. Okay. All right. I'm so thankful that you guys are watching this series. Seem to have struck a chord with this studio monitor design stuff. So let's keep it going. If you guys have friends that you think might be interested in this stuff, share the love. Tell somebody about this series. Watch it with them. Make popcorn and eat it while watching. My face. I'll see you guys in the next one. We're gonna actually build this sucker. All right. Not peace. Don't say peace. Bye. Bye.